now, to get the presentation started, I will turn the mic over to Marilyn Walker and Peter Lilienthal.
Thanks, Tricia. So I'll start with just a quick roadmap of where we're going to go today. And starting with an overview of HOMER Pro, its history and its focus. Then a little deeper dive into what it does. What are the main applications that you can use it for? I'll briefly cover the licensing options. And then at the end, Peter Lilienthal, who's the creator of HOMER, will take over and walk you through some of what he sees as some of the most important new features and ways to use it. HOMER is actually an acronym for Hybrid Optimization of Multiple Energy Resources. At its core, HOMER is a simulation engine. It simulates the operation of an electric power system for 1 year, hour by hour, or even minute by minute. And then at each one of these time steps, HOMER looks for the most cost-effective way to meet the electric load. So that simulation step tells you how one system operates. And then there's an optimization step that simulates hundreds of different systems to find the least cost solution overall. And then HOMER also has an option to do sensitivity analyses. And these allow you to look at the impact of variables that you can't control and how these might affect system design and costs. Examples of these might be the price of fuel, price of storage, maybe your wind speed data. So our focus today is on HOMER Pro, and that's our flagship product. But I also want to mention that we also now have another product, HOMER Grid, that was designed explicitly for behind-the-meter systems in grid-connected markets. And in these markets, demand charge reduction, time of use rates, and other factors or combination of factors matter most. And so it's a slightly different approach than HOMER Pro. So we're still actively developing both these products as both the markets and the technologies grow and change. Talk a little bit about the history. HOMER originated at the U.S. Department of Energy's National Renewable Energy Laboratory here in Colorado, following the 1992 Earth Summit in Rio. It was part of a program there called Village Power that was intended to assist with rural electrification in developing countries. Peter Lilienthal wrote the original HOMER in a third-party program, GAMS, that was designed for optimization analysis. And then in 1997, a Windows version was created. And in 2002, version 2 of HOMER came out, adding grid connectivity, combined heat and power, and multiple generators. A big step forward for HOMER was in 2009, when HOMER Energy LLC was formed and signed a commercialization license for HOMER with the exclusive rights to develop and distribute it. And so that gave us access to a lot more resources than were available at NREL, where we were, anyway. So HOMER Pro was first released in 2014 with a new interface, a much improved licensing systems, and at that point, we really made it scalable so that we felt like we could continuously improve it more easily. And that's what we did over the next 5 years. We had 13 major releases since then. Some of the more notable features were the addition of unreliable grid that a lot of people have been asking for, and the ability to model your own control algorithm in MATLAB. In 2018, then we released HOMER Grid. And in 2020, UL acquired HOMER Energy LLC, which is where we are today. So there are 3 main steps in using HOMER to design and optimize your microgrid or distributed hybrid energy system. First, you set up information on the economics, such as interest rate, your energy demand and load profiles, your location, which allows HOMER to then download renewable resources such as solar radiation and wind speed from the internet. And you also specify which system components you would like HOMER to consider, what might be possible for you. HOMER then steps through the three nested processes we talked about: simulation, optimization, and sensitivity. And then it provides very detailed results on the economics of all the systems and exactly what's going on in every hour or every minute. So we call HOMER Pro our Swiss Army knife because of the number of different things it can do in one package. Peter's going to demonstrate some of the capabilities, focusing particularly on some newer capabilities and on things that are easily really useful and powerful, but often overlooked. But just to kind of give you some idea of how many things it can do, HOMER Pro can handle 6 different load types, 14 different types of generation, storage, and controls, each of these with its own set of options, 9 different resource types, including a custom resource, and 7 other categories of control, again, each with its own set of options. So doing a little quick math, that's literally thousands or tens of thousands of possibilities within one program. HOMER has really helped define and create the microgrid market. It's been downloaded by over 240,000 people. These people belong to about 40,000 commercial and industrial organizations, 7,000 different universities and colleges, 1,000 government agencies, 1,000 nonprofits worldwide, and you can see really these dots are all HOMER runs. Over 90,000 different projects have been modeled, and over 3 million models have been run, and that's just since the release of HOMER Pro in 2014. So we divide the major markets and applications addressed by HOMER Pro into 4 broad areas. The first is remote power or village power, which was the original HOMER use case, but now can include other applications such as field research stations, military bases, cell towers, and data centers. Then there are island power systems, larger systems with multiple generators, often with distribution systems. This is Wales, Alaska. It also does grid-connected systems. And finally, research and teaching has become a really major area for HOMER Pro. So one of the things we've done to make the complexity of HOMER maybe a bit easier for our users is to make some of the features available as add-ons. So depending on which stage you are in with your project and what your specific needs are, you can tailor HOMER Pro to fit them. We currently have 9 different add-ons available. You can purchase them either individually or as packages, and I'm not going to go into all of these today. They're all on our website, and certainly our support and sales team are happy to help you figure out what you need. We also have lots of licensing options available so that, again, you can just pay for what you need. I already mentioned the add-on modules in the last slide, and these unlock certain features that not all users necessarily need. We've also bundled these together for major applications to make it a little easier, or you can create it exactly what you want, how you want. We have multiple pricing tiers available, multiple seat discounts, because we want HOMER Pro to be accessible anywhere in the world. Licenses are available either for a single user, or if you have a need to share licenses, we have that available as well. And we also have a range of time spans, licensing time spans available from as short as 1 month to as long as 3 years. So before I turn it over to Peter, I just want to mention that we're just about to release another major release, an exciting new feature, the ability to turn your HOMER analysis into a branded proposal, something we've been getting asked about for years. So if you have a current license, either paid or trial, you'll get an email about this when the beta is ready. And if not, and you want it, make sure that you reach out to us and get a license so that you can try this out. So I believe Peter's going to demonstrate how to use this new feature, so I'll turn it over to him now.
So I'm just going to talk a little bit before we jump into a demonstration of the software, but I think it's really important to point out that there's 2 very different ways that HOMER gets used. It was originally a research project at the National Renewable Energy Lab, which is a research organization. originally we did a lot of high-level analysis with it. For example, how much better does the technology have to be? What applications and markets is it applicable for? What sort of price points does it have to meet? That's also useful for policy analysis, like is this a promising technology to promote and develop a policy around? The cost structures are really different for hybrid systems than for traditional technologies, so the tariff and subsidy structure should probably be different. So there's a lot of high-level analysis that's been done with HOMER, and that's well suited for. And for this kind of analysis, and also for early stage of project development, you just want a conceptual design. You don't really want details, can be actually distracting at this point. So we have generic components and generic load profiles to either get you started or just be representative. You also don't want to be too explicit about sizing. You don't want to come into the analysis with preconceptions. So we created an optimization algorithm that doesn't require you to have any constraints or preconceptions. You just let it find the right sizes, et cetera. And because there's a lot of uncertainty in the early stage of project development, or if you're just doing again a high-level analysis, sensitivity analysis is really important. So we built it into HOMER, and I think it's one of my favorite features of HOMER, and it's particularly valuable at this higher level conceptual analysis, where the goal is insight. You know, I got my modeling started at Stanford's University's Energy Modeling Forum, and their seminal paper was modeling for insights, not numbers. And so that's this particular use case, high level. We're just trying to understand and get insights, and also to educate ourselves. So if we are developing a project and we want to talk to vendors, they hate it if we come to them and we don't know what we're talking about yet. It's a much more valuable conversation if we've done some analysis and we have some idea of what we're talking about. So that kind of insight is the goal at this high level analysis. But then after you've talked to the vendors and you've got specific components that you're looking at, and you've talked your boss into devoting the resources to developing good data, the conceptual analysis is really useful for that conversation, but you've got the good data, and now you want to do a more detailed analysis where accuracy is the goal. Bankability is sort of the buzzword. And so HOMER lets you put in specific components with specific sizing choices. We have a cost table that allows you to say, well, you know, if I buy more of them, the price goes down, et cetera. You can upload measured load data, measured resource data. So that's a very different type of analysis, but we allow you to put in HOMER data in both ways. For this more detailed analysis, you really want accuracy. So I like to highlight, these are two very different ways to use it, and we think it works well for both, but it's worthwhile to recognize those are two different things. So now I'm going to give a demonstration of just a couple of features that I think get overlooked a lot. We have this deferrable load module or controllable load. It's originally thought of for water pumping, but it could be ice making. It could be any kind of controllable load where you have some flexibility about when you meet the load. And what's really important in the energy access world is when does it make sense to extend the grid? Like, we could do this standalone system, but is that actually cheaper than just extending the grid? And so HOMER has that capability, and it's a little hidden, so I wanted to show off where that is. So those are for the smaller systems. For larger systems, you'd have multiple generators, and we created a dispatch strategy specifically for multiple generators, and it's a little different, and I wanted to just show that off because many people may not know about it, and if you are doing a larger system, you really want to use this control strategy. And when we can do combined heat and power, I probably don't have time to go into a lot of detail on that, but it's worth mentioning. And I'm going to show this proposal writer that Marilyn mentioned, and it will be available within the next week or so. So let me jump right in, and I have to pull up a different, so now you should be looking at HOMER, and we're looking at a water pumping application in the deserts of Utah. And the idea, we're going to keep it really simple just to demonstrate this capability. So we're just going to compete a simple PV system against the grid. But the main thing I want to demonstrate first is this concept of deferrable load. So you find that under load deferrable, or you can click on, and it pulls up this screen. And we try to keep things simple, so for quick analysis, what we're saying here is that the water pump is 750 watts. We're saying it's either on or off. It can't run at park load. Now the load on it is in kilowatt hours per day. So basically we're saying we can meet the annual average water requirement by running this pump for 2 hours a day. But we're saying there's some seasonality to it, and the water demand is higher in the summer, which is we've laid out over here, but it averages 2 hours of pump use a day. But HOMER is going to pick when to provide that power. And then how big is the tank? That's the really important question. And so we've said here that the tank is good enough for 4 days of average consumption. So it's 6 divided by 1.5, 4 days. So that's it. Keep it simple, and we run the model, and it says you need just let under 2 kilowatts of PV for this really simple system. Now we could add batteries, add controllers that allow you to run the pump at part load or whatever, but we're just keeping it simple to demonstrate this capability. Now we want to compete that against the grid. So we go to the grid module here. And as Marilyn mentioned, we can do grid connected projects, and we have different ways of setting up the rate schedule. This is not a grid connected project. We have a totally different model, HOMER grid. If you really want to get into, if you really to do really focus on grid connected projects, that's the tool to use. But you can do a simple analysis here. What I want to show, though, is the grid extension, which is completely different. It's not a grid-connected system. It's competing the grid extension against the hybrids or the standalone system. So it's either or. It's not connected to the grid, but it's saying, so we calculated what it would cost to do the standalone system, and now we're going to calculate what it costs to extend the grid. And we're going to do it in the simplest possible way. What's the grid extension cost? $1 per kilometer. What's the cost to maintain it? That's dollars per kilometer per year. And what's the cost of power on the grid? We're saying 14 cents here. So that's what, with that, we can go into the results. Double clicking on the result here pulls up our simulation results. And on the grid extension tab, you see the standalone system, doesn't matter how far you are, it's going to say it costs the same amount, so it's a horizontal line. But the grid extension is a function of how far it is, right? And here's the cost of the power, but the bulk of the cost is the poles and wires. And what this is saying is, if you're within 420 meters of the existing grid, it's cheaper to just extend the grid. But if you're more than 420 meters from the existing grid, the standalone system is preferable. So that's a really important result when in the energy access market, where they're trying to figure out, well, where should we extend the grid, or should we use these new hybrid systems? So the answer is it depends, and this gives you that answer. So let me talk about another capability that I think may get overlooked. I have to pull up a different HOMER file. And that is our multiple grid dispatch strategy. So again, I've created a super simple, there's not even any renewables here, of imagining you're powering a small island in the Grenadines. And to get to the components, so you can either click on generator under components, or you can click on one of the generators here. And you can see I have 4 generators. A peak load is 742 kilowatts. So an 800 kilowatt generator is probably good enough if it would meet the load, but if we can stage different size generators, maybe that's more efficient. I mean, it probably is. So that's what we're going to model. And I've created these generic generators here the 800 kilowatt generator, 400 and 200. And these are what we call, we have two different kinds of generators. So these are size your own, so you can put in any size you want here. And these are the sizes I've picked. Now we have a library of generators, and it's quite extensive. So there's the Caterpillar generators, the Cummins, Danvest, Rolls-Royce, it's quite an extensive. And those are specific generator models. So you can't size your own. They come in specific sizes. So those are, and so for that kind of generator, the UI looks a little different. It doesn't have this search space. Instead, it is a fixed capacity. This one's 100 kilowatts. And you can either include it in all the systems or ask Homer to tell you whether or not you should have it in the system or not. But it's a fixed capacity. So we have these 4 generators. And if you have multiple generators, it's really important to pick the right control strategy. So we have several different control strategies, but the one for multiple generators is called generator order, and this mimics the way we found utilities actually think about dispatching or committing their generators in a merit order. And so what Homer does is it starts at the top of this list and says, can I meet the load? And if not, it moves down the list. So the first row here is generator off. Now it's obviously not going to work because we don't have any renewables or batteries. But if we had enough renewables and batteries, you might be able to run for this time step, 100% renewable generator off. Homer quickly determines whether that works or not. In this case, it wouldn't, and it just works down the list. So will the 100 kilowatt generator do it? No. The 200 kilowatt generator? No. The 100 and 200 together, that's 300 kilowatts of capacity, maybe, and it works its way down the list. And here's the 800 kilowatt, that would probably do it. I've kept going, so here maybe if you parallel the 800 with the 100, you get 900, and we can add rows as many as we want, and we can set this up any way we want. I've done it in sort of a hyper rational way, but you want to mimic the way you think the system's, or you either have been operating the system or think it's going to operate. Now, do I have time to talk about operating reserve? Because that's also really important for these larger systems. You want to have
plenty of time, Peter. Sorry.
Okay, good. And I hope I'm not talking too fast. But operating reserve is super important because just because let's say the load is 742 kilowatts, a 742 kilowatt generator is not going to do it because the load's going to fluctuate during that hour. And if you have renewables, it's going to fluctuate even more, the net load. So operating reserve is really important, and I do want to talk a little bit about it. So you find it here under project constraints and operating reserve. And when you add renewables, they're variable, you have to probably add additional operating reserve. And we can do sensitivities on this because it's not something that's easy to predict how much operating reserve you really need. So typically people will start off very conservative, and then Homer can tell you, well, how much is it costing you to be that conservative? And over time, you might want to get a little more aggressive as you get more experience with it. So Homer will, when it says on the previous screen when I was talking about can it meet the load, and the operating reserve? And if it can't, it moves to the next row. One thing that I think Homer does that needs just a tiny bit of description, explanation, is a lot of utilities say, well, I always maintain 100 kilowatts of operating reserve, and it's a fixed amount. And you can do that. We have operating reserve as a percentage of the annual peak load. So the annual peak load is a constant, and you have to say, well, 100 kilowatts is what is that as a percentage of peak load? So you have to calculate that peak load, that percentage rather, that goes in this field in percentage terms. So it's a little different, not that hard, but you got to think about it a little bit. So between those two things, you can have quite a lot of flexibility about how you dispatch or how you commit the different units in a multiple generator system. And it's just computationally much, much faster than the other dispatch strategies, which are really designed for single generator systems. So if you have a multiple generator system, use the generator order dispatch strategy. That's the main point there. So the other thing I did want to show before we get to questions and answers is the proposal. So here's our results. We didn't do a sensitivity analysis in this case. Here's all the different, well, actually there's a lot more systems that we looked at, but you can see it, we rank them by net present cost and cost of energy. So the least cost system is at the top. And yes, it does make sense to have all these generators so you can match things perfectly. And you can see it has the least fuel consumption as well in this column here. If by double clicking on a row, it pulls up the detailed simulation results. There's a lot here, and there's time series plots that we can look at of how did it actually operate, which generators came on when over the whole year. We can look at load duration curves. We can look at a lot of stuff that I don't want to show it all off, but I do want to show off our new proposal writer. So by clicking on this button, we can enter some information that will get put into the proposal about who we are, who the client is. We can put in testimonials, etc. And we can customize it, and it can come in different forms depending on what paper size you want to use. And I've got let me pull it up here, and this is what it looks like. So this is the information we put in there. I picked some silly stuff to talk about, and I just want to just briefly show you. You should look at this yourself, but it's got a lot of good data here. Here's the testimonials, and I'll just slowly just scroll through it to get you an idea that there's a lot of data here, and then it's formatted in a format that makes a nice proposal. And at the bottom, a glossary, information about us, information about you. We could put in some custom charts. So we created this proposal format for our other software, HomerGrid, and released that a couple of months ago. And now, within the next week or so, this will be available as well. So I ran through that quite quickly, and I thought I'd send it back to for questions. And
Wonderful. Thank you so much, Peter. Marilyn is preparing questions for us now. And while she's doing that, I just wanted to share some information, excuse me, while I share my screen, about the fact that we do get questions about training and support services. Homer Pro can do a lot of stuff, as Peter and Marilyn just showed, and it's really a very powerful tool. So to get the most out of it, we offer both training classes and support. We do have a number of training classes that we recently expanded, and we also offer premium support and consulting, or if you prefer, our advisory services can do the work for you. You can find out more at gethomertraining.com, or you can contact us through support@homerenergy.com. So we are going to go ahead and go to questions now. Marilyn has been collecting the questions that you all have been sending in as the presentation was going. And so Marilyn, I'm going to turn it over to you. What do you have for us?
Yeah, and we may go back to Peter just because I think some of these things might be answered well by having Homer in front of us. So Peter, maybe if you just make sure that you still have that running in case we need to switch presenters.
Sure.
And so I'll actually just start with like a really simple one. which I'm sorry we didn't do this really basic thing, which is how do you get started with HOMER? Go to our website, homerenergy.com. And yeah, Trisha's got it right up there. Free 21-day trial is there, and go ahead and get that and get started. There's a tour, there's all kind of help available. And we also have a help desk and a support, a manual. So we've tried to put the information out there. We know it's not always there. And like Trisha said, we also have training programs. So don't delay, just go ahead and give it a try. It's do it. Okay, so gosh, where to start? Okay, here's a nice simple one. Can HOMER accept solar data from other programs?
Absolutely.
Yeah, so how does that work?
Well, so should I show in the software? I'm happy to do that. And in
you talk about it, whatever's easiest.
Yeah, could I take the screen back? So hopefully you're seeing the opening screen of HOMER now, right? Am I showing the opening screen?
Yes.
Yes, you are.
Okay, so when you first open up HOMER, you get this screen here that has there's a tour you can take, there's a setup assistant, and you can get rid of this as well. But the setup assistant actually is a great little wizard that walks you through getting started, and then the tour, you can also get to it up here, is similar, multiple steps. So that's a really quick and easy way to get started. We've got a huge help facility as well. Showed up on the other screen, which it's huge. So I'm not going to go through it all, but if you have any questions, it's got a search. It's like a big, huge glossary here. So, we get a lot of support questions, and we have a whole support group. Happy to answer your questions. Most of those questions actually probably can get answered in the help file if you just search for it. So that's question number one. Question number two is about importing solar data, right? So if you go here to solar, we've already got data in here, but you can import the data here in multiple formats. And you can clean it up if there's gaps in it, etc. We have an integration now with Helioscope and PVSYST, so that if you have PVSYST data, it's really quite straightforward. And what we're doing in that case is not just importing solar resource data, we're reporting the PV output data from PVSYST. And likewise with Helioscope, we have a little wizard, and it just asks you for your Helioscope login information, and then, which I'm not going to do right now, but then you've already got data in Helioscope. You just give it the right identifier, and it pulls that right into HOMER. So you can import data from other measured solar data, like if you measure it yourself, or if you have a data file of the resource data, you just import it. Or if you're using either of these pieces of software, you can import not just the resource data, but the actual PV production data. And I noticed, as long as I've got the microphone, I noticed a question about carbon, comparing the carbon footprint of the hybrid system versus the grid extension, and we can do that on the grid component here. We can list what's the emissions profiles of the power that you get from the grid, and we can put in carbon pricing, or we can put in limits on carbon consumption, and we can do that for the hybrid system as well. So we can give you credit for carbon reduction. Sorry, I hijacked.
Yeah, and just to be clear, so you can look at emissions in any system in HOMER, right?
Right.
Yes, HOMER's calculating the emissions based on whatever data you're able to make available to it on that. So yeah, another question that I'm seeing coming up, maybe the grid extension part, you might have gone a little fast there. Can you talk about the difference in just, grid connectivity versus exactly the question being answered in grid extension?
So the question being answered that I was trying to answer here under grid extension was, okay, we've got a need for power somewhere, whether it's a village or livestock watering tank or a research facility, whatever. We've got a need for power somewhere where there is no power, and we could extend the grid to it, and that's people know how to do that. That's been what's the traditional approach, but those poles and wires can be expensive. Or we can put in this new idea of using renewables, and maybe it's a hybrid system. I mean, I just demonstrated a really simple PV system, but more typically you'd have a hybrid system, and that and it could be, let's say it's a village, and they have a regular load, like normal residential load, and there's a school and other facilities there, and they also have water pumping. So on our load component, am I showing my screen? I think
Yes.
I am. We have both. We can have a high priority load and a low priority load, or a commercial load and residential. We have two different kinds of load and a deferrable load. So we can do. I did a really simple thing with just water pumping, but it could be water pumping in addition to other loads. And the question is that we're trying to answer is, well, we could design a hybrid system for this load, or we could extend the grid, and which is less expensive. And so HOMER will calculate what's the best hybrid system to use, and what does that cost. And then this module right here is just a really simple way of calculating, well, what would it cost to extend the grid instead of building the hybrid system. So you need to, so that's the question we're answering by what's the poles and wires cost, what's it cost to maintain the grid, and what's it cost to provide the power on the grid. And then we get this result that I showed here, that shows where the break-even distance is. If it's closer than that, the grid extension makes sense. If it's further away, the standalone system is less expensive. So I hope that answered the question. Not sure
Yes,
what
thank you.
more I can say.
Actually, before I dive in, back to the next question for you, Peter, I think I can answer this question. So I've seen several people ask about currency symbols. I think you can use any currency symbol, correct? But what if Windows handles it?
Yeah, hopefully I remember where to do that. I thought it was here.
I don't, so that's why I was saying I think it does that.
I hate to say it, I don't do that very often, but currency, there we go. So we have a big long list of currencies.
Yes, yes.
And the only thing, and you can use any currency symbol you want, but I do want to caution, if you can't mix two currencies together. If you're gonna do it in whatever, Vietnamese dong, for example, everything has to be in Vietnamese dong.
Right.
So that's important to
So that was kind of a backdrop to the next question, which is just seeing a lot of questions here on costs. And we get these questions a lot, like where do the costs in HOMER come from? And specifically, if you could talk about like, using like some of the more advanced cost tables where you can look at economies of scale, and also how about like costs like other development costs such as cabling, operations and maintenance costs? Where do those numbers come from?
Okay, this is a big topic. So where should I start? I'll start with the first thing you mentioned, which is where do our costs come from? So we have this methodology, we have this model and software, and we provide the model and software. Trying to maintain a cost database that's both up to date and applicable. HOMER is used in every country in the world. Costs vary dramatically from place to place, and from supplier to supplier, really, there's really no way we can provide anything close to a comprehensive cost database. So And I apologize for that, but I don't see any way around it. So let me just, using PV as an example, show a couple of things. First of all, you asked about O&M. So every component has O&M, and a replacement cost because it has a lifetime. Where's the lifetime? There it is. So we need to set aside money to replace it. This is more applicable for batteries and generators because PV lasts for a very long time, but we do it for every component. So replacement costs can be different than the capital cost. Maybe you don't have to replace everything, just, depending on the component. And the O&M is important. Boy, I can go into a lot of detail here. O&M for generators is based on operating hours, and O&M for PV and inverters is based upon calendar time. And that's important. If you hit the More button here, it pulls up our cost table. This could get a little complicated, but this is where we can put in economies of scale. So let's say it's $3,000 a kilowatt, but if you buy 2 kilowatts, the second kilowatt is only $2,000 dollars per kilowatt, and we can put in as many rows as we want here and make this as complicated as we want, or we can base it on actual quotes that we have. So that's if you have actual quotes. If you're really not sure what things are going to cost you, you can do a sensitivity on it and say, well, what if that price is too high and I can really get it for 25% less? So sensitivity analysis, that's a whole nother topic. But that's really useful if you're not really sure what the price is, or you're just in the early stages, or trying to figure out what the price ought to be. Then there was another question about other costs. So all the costs have to be somewhere, right? So the PV cost needs to be not just the modules, but shipping. Did you have to pay import tariffs? Do you have to pay a dealer margin? Do you have to installation, the racking hardware. Likewise, for each component, it's not just the component itself. It's what does it cost to actually totally install the cost, everything included, broken down by components. But then there's some costs like the distribution system or the marketing, the early development costs that aren't really, they're going to be the same regardless what the system is. They're not a function of the size of a component or anything. So if you go here under economics, we have these two categories here: system fixed capital costs. So that's where I'd put in if I have to upgrade or build a distribution system, if I want to put in the upfront costs of early development, going out to all the early development costs. If it's a one-time cost, I'd put it here under capital cost, system fixed capital cost. But then if I have things like operator salaries or administrative costs that are going to be ongoing, and again, don't depend on the size of the system, I put that here. And these don't affect the optimization of the design, but they do affect the total cost and the cost of energy and the cash flow, et cetera. So, that was a quick overview of costing. I hope I covered all the important stuff.
Yeah, that was great. I do one more quick cost question. I hope it's quick before we go on to another area. But I think this is about, people are talking about resale value, which I believe we're talking about salvage cost.
Yeah, we use the term salvage value.
Can you show that, where that is, and how you set that?
Well, we don't set it. Every component. I'll go back to PV for a minute. Every component has a lifetime and a replacement value. And so let's say the project life was 30 years and the PV replacement time was 25 years. So Homer's going to say, well, 25 years in, we're going to replace the PV array. And then 5 years later, the analysis stops 5 years later. Well, we've got an almost brand new PV array. So that has, there's different names for it. And I'll show you where you find it. Sometimes it's called terminal value. Sometimes we call it salvage value. That sort of implies you're actually going to take it out, which we probably aren't going to do. Resale value, I guess, is what the question asked. They're all, I think, synonyms. And it shows up in our cost table here. Let's see, it's salvage value. in this case it's 0 because I wasn't planning to show this, but it's really important because when you set an arbitrary project life, well, in all likelihood, the project it is not going to go away. But if you just replaced a component, we don't want to penalize the project economics because of this arbitrary time issue. So we want to give it credit for it's undepreciated or partially depreciated. So we want to make sure that the economic analysis doesn't, you know, inadvertently penalize something just because of the timing of the replacements. So the salvage value is really important, even if you're not actually going to salvage the components. So another way to think of it is just terminal value from an analysis perspective. So I hope that's a good explanation.
Yeah.
That is a question we get a lot, and we probably should have named this terminal value instead of salvage value, but that's
okay, great. Thanks. So another questions, these have been, there's so many great questions, and I need to let everybody know we are not going to get to all of your questions, but I'm trying to kind of group them a little bit. And that's why we have, that's why we have a support desk that if they can either point you to where your question is or answer it directly, point you to an article. So another one is actually earlier, so that sort of the optimization approach that HOMER has, which has also evolved over time. Could you just talk about that a little bit, about the different algorithms that it's using?
Sure.
How that works?
This is another really huge topic, but I did see there were a lot of questions about it. And it's important to think there's sort of two levels of optimization going on. There's what we call control or dispatch. Each time step, what should HOMER do in terms of charging and discharging batteries, turning on and off different generators, et cetera, meeting different loads that are controllable. And like I said, we have 5 or 6 different control algorithms there. And you can create your own, either in MATLAB or C++. That when we usually call that control or dispatch, but it is a form of optimization. What we more typically use the term optimization for is at the capacity level, not at the each time step operational level, but at the, how big should the PV array be, how big should the battery bank be, et cetera. And we've gone through multiple different algorithms. The original, Marilyn was talking about, originally we used GAMS, which is a commercial optimization software, when we weren't happy with it. And linear programming is clearly inadequate. And by experience from a long time ago, that's really obvious. But so we have, so for a long time we had a search space, which is a sort of a brute force approach where you just give HOMER lots of choices of sizes, then it tries all the permutations. We had some smarts about it so that we knew if something was infeasible, anything smaller than that was infeasible. It was a little bit smarter than just exhaustive check all the possibilities. But then we created a new optimization algorithm, and it's trademark HOMER Optimizer. And it's a little hard to describe in words quickly. Because each iteration is itself a whole simulation. So, but it's basically, so I don't have a good way of describing it, but it's a smart way to search through the space. Maybe I should have a whole webinar just on that. It's of great interest to people, in operations research and, higher level math, industrial engineering kind of academic programs. Not that much of interest to practitioners in the field. But we put a lot of thought into it. It's just a little difficult to describe in words. We're very happy with it, though.
Great. Gosh, so many great questions. And I just want to thank you to all the people writing and thanking us for thanking us for that. We really appreciate it. It means a lot to us. And yes, whenever we do this, we always think, gosh, we need to do this more. There's so much to it. And just so you know, we are always working on that. I know Trisha and I are working together to try to get some more, recorded trainings and information out there. So we really appreciate it. And I'll try to talk Peter into doing more of these getting on, because he's always really fantastic with that. Okay, so actually another one, and this relates to some of the the updates we've made to Homer Pro and all those major releases, and that is battery degradation over time.
Right.
Talk about that in Homer.
Yeah, well, so we have 3 different battery models. An ideal model, which is just super simple and doesn't really, it's just the ideal battery. So if you have no data at all, but it's overly optimistic, really. We have the original kinetic battery model that originally came out of University of Massachusetts. NREL's been using it for a long time, and that's the most common one we use. We also have an advanced storage module. I could show that in a second, but I just want to point out, I happen to notice what one question says, how many generators max can you use? And there's the answer to that question, if that person is still there. Let me see if I can show the advanced storage module. So if I go here into storage, if I go here in the library, that's the best place to do this. Whoops. And we'll take this here, ASM, Advanced Storage Module. It's really, and we can create new ones by copying this and changing it. So it's got quite a lot here. Here's its capacity curve as a function of discharge rate. Here's how that varies with temperature. The cycle lifetime as a function of depth of discharge. So that's a pretty standard thing. How does the lifetime vary with temperature? This one isn't very interesting, but that's there's a lot here. And if you do when you talk about degradation, you really need to be talking about our multi-year capability. And so if you are using multi-year, it instead of modeling 1 year, it models how, like in this case, it would be 25 years. And you're using the advanced storage module, it will degrade the battery according to the inputs on this advanced storage module over the 25 years in this case. I don't have time to set it up to actually demonstrate it, but it will handle battery degradation if you're using multi-year, because it's not going to degrade much in 1 year, and if you're using the advanced storage module. So that's sort of a more advanced topic, really, but it's actually very, very important.
Yes.
If even with the other ones, though, what is really important, even if you're just using the simple model, the battery lifetime is in kilowatt hours throughput. Now with the advanced storage module, it's more complicated than that, but Homer will calculate the throughput on the battery and calculate when the battery is going to wear out based upon the manufacturer's data about cycle lifetime, depending on depth of discharge, et cetera. And so Homer will calculate when the battery needs to be replaced based upon that manufacturer's data, even if you're not using advanced storage module. But it'll assume it has full capacity until it's ready to be replaced, unless you're using the advanced storage module. Oh boy, big topic.
Thanks, Peter. So actually, we're pretty much out of time, and so I'm going to challenge you to do this in like 1 minute. Just talk about editing or adding components. Like you have a component that's not in our library. How do you?
Yes, you can create your own. You can create your own components. The easiest way to do that is to take something somewhat similar, make a copy of it. Oh wait, I haven't clicked on something. Whoops. All right, make a copy of it, and see it's not grayed out anymore. Now you can change all the inputs. So you can add your own, and you can create your own library. So if you look down here, the ones in bold are ones that I've created, and the bold ones actually show up. in here, in this drop-down box, has our generic ones, our market access partners, and any ones you created yourself. You have a personal library. That's the old ones here. So you can create
great.
your own components. Yeah.
Thank you. Okay, I'm going to turn it back over to Tricia. Thanks, who's going to say goodbye, and just thank you, Peter, for all those great questions.
And thank you, audience.
Everybody who asked them. Yeah.
Thank you so much, Marilyn, and thank you, Peter, and thank you, everyone, for such excellent questions. It's always illuminating when people who are using the program or considering using the program ask questions about what they would like to know, and it really enhances the demonstration. So thank you for that. Before we go, I did want to let you know about some upcoming events. Coming Thursday, August the 13th, join us for a multi-presentation webinar on optimizing design and mitigating risk in mini-grids and distributed generation. We will have a special focus on Africa for that webinar. We'll have 3 experts to present on risk mitigation from obtaining financing through design and operations. Presenters will be Dr. Peter Lilienthal, James Trudeau, who's the Global Business Development Manager at UL, and David Minzer, who's the Principal of Starboard Energy Advisors. And you can watch for a registration link in our follow-up emails. And we're really excited that the 8th annual HOMER International Microgrid Conference is coming October 12th through 16th. It will be 100% virtual and free to attend. We are putting together an outstanding agenda of presenters over the course of those 5 days. The speakers will present the latest advancements and use studies in the role microgrids play in resilience and grid-connected systems and emergency response, energy for islanded communities, energy access, off-grid controls, developments and regulations, and technology advancements. There is a sneak peek of the agenda on the conference website, microgridconference.com. Registration will be opening very soon, and sponsorship opportunities are now available, so please be sure to visit the conference website, microgridconference.com, and get on our mailing list to stay up to date. And I want to thank you again for attending today's webinar. If you did not get your question answered, please send it in through your sales rep or visit our support desk, and we'll be happy to respond to that. And please watch for an email in a few days with the recording of this webinar, and we hope to see you again in August and at the conference. Thank you so much.